Hey everybody, today we're talking about solving quadratic equations by finding square roots. So let's remember this from way back when we are talking about a number, it has a square root if its factors are a number times itself. Okay, the symbol that looks like this is called a radical. So we would say the square root of 4 equals 2 because 2 times itself equals 4. Okay, so let's talk about some properties of some square roots. So the first one is called the product property. And we know the product property says that the square root of a times b is equal to the square root of a separate from the square root of b. So for example, if I have the square root of 18, that's like saying the square root of 9 times the square root of 2, where here I know the square root of 9 is just a 3. This is saying like 3 times the square root of 2, which cannot be reduced again. The quotient property says that the square root of a over b can be rewritten as the square root of a separate from and divided by the square root of b. The only restriction here is that b cannot be 0, because if we take the square root of 0, then it's going to be 0 on the bottom, and we can't have a 0 on the denominator. So for example, if you've got the square root of 2 over 25, we can separate these as the square root of 2 over the square root of 25. And I know the square root of 25 is just a 5 on the bottom, and this is a square root of 2 on the top. So let's talk about how we can do our own square roots and things. But first, before we do that, we're going to work on our perfect square list right here. So our perfect square list are the numbers that have a perfect square root, meaning they go evenly. So 1 squared is 1, that's a perfect root. 2 squared is 4, that's a perfect root. 3 squared is 9, which is a perfect root. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. 15 squared is 225. And 16 squared is 200 and I think it's 56. Okay, so that's the beginning list of perfect square numbers. So when we're simplifying roots, we are going to be looking for numbers where these values or perfect square list is one of the factors. So if I'm looking at the square root of 80, I'm going to look for factors of 80 that are in this list, okay? So I know 80 can be split up as some root times some root, and I'm looking at those values of 80, and I can see, and if I'm not sure, I can always use a calculator, but I know that 16 right here is a factor of 80. So I know 16 times 5 is 80. And I also know that if I take this root of 16, well, that root of 16 just becomes a 4. So this is just the 4 root of 5. So that's how we simplify it using a radical. Here, I see the root of 6, which cannot be simplified, and the root of 21. So if I combined them under the same root, because they're equal, the root of 6 times 121, I get the root of 126. The root of 126 can split up into the root of 9, because I know root of the 9 can multiply by 14 to give me 126. Now the root of 9 is really just, looking over here at this list, is just 3. So this whole thing can simplify to 3 times the root of 14. All right, let's go to the next one. So I know that the root of 4 over 81 can be rewritten as the root of 4 divided by the root of 81. Well, I know the root of 4 is right here on the perfect squares list is just 2. And the root of 81 right here is just 9. So we can simplify it like that. Here we can say the root of 7 over 16 can be split up as the root of 7 over the root of 16. I know that the root of 16 is just 4. So this is just the root of 7, which cannot be simplified over a nice perfect 4. Okay, so there's this rule, and it says there can be no roots in a denominator. So if you have a root in the denominator, what do? So in this case, if there's a root in the denominator, we have to use what's called rationalizing. Okay, where we're going to multiply by what's called the conjugate. So it doesn't work. The conjugate is what we would use for these two. Okay, so if your denominator looks like the root of b, you're going to multiply by the same thing, because we know the root of b times the root of b is just b squared. And remember, when you multiply, you're going to multiply it by the top and the bottom. Okay, so we're going to multiply the numerator and denominator by the root of b. If we're dealing with a plus the root of b, we're going to multiply it by its conjugate, which is the same terms, but the opposite sign in the middle to both the numerator and the denominator to cancel out the root in the denominator. And then lastly, if you have a minus the root of b, we're going to use the same terms again, but the opposite sign in the middle. Okay, so for example, if I'm simplifying the root of 5 over 2, I'm going to simplify this as the root of 5 over a separate root of 2. This is okay, but I can't have a root in the denominator. So now I'm going to rationalize. So if I've got the root of 5 over the root of 2, now I'm going to multiply it. So I see the root of 2 is just the root of a number, which means I'm going to multiply it by this right here. So I'm going to multiply by the root of 2 on the bottom and the top. What that does is as I multiply across the bottom here, the root of 2 times itself is really the root of 4, which we know can just simplify to 2 on the bottom. And then as we multiply what's going on here up top, the root of 5 times the root of 2, you can put 5 and 2 in the same root, which is just the root of 10. And that's perfectly fine, and there's no root in the denominator. All right, let's try another one. So we've got 3 over 7 plus the root of 2. So we see that there's this root 2 in the denominator, which violates our rule. So we are going to rationalize. So remember, when we see something that looks like 7 plus the root of 2, that looks like this here. So we're going to multiply it by its conjugate right here. So let's go ahead and set this up. So if I've got 3 over 7 plus the root of 2, I'm going to multiply it by its conjugate on the bottom. So instead of a, it's 7 root 2, and then instead of plus, we're going to put a minus here. What that's going to do for us, it will actually cancel out. Remember, whatever I multiply to the bottom, I'm also going to multiply to the top. And now we're going to expand this so that we can simplify. So we're going to essentially basically FOIL this on the bottom. So we're going to go 7 times 7 is 49. 7 times negative root of 2 is minus the 7 root of 2. Root 2 times 7 is a positive 7 root 2. I'm going to try to see if I can put this in here. And then the last term is, I'm going to do this in red, is root 2 times a negative root 2, which is like saying root 2 times root 2, which is just the root of 4, which is just 2. Okay? So that's the bottom. Now let's simplify the top. So we're going to go 3 times 7 is 21 minus 3 times the root of 2 is 3 root 2. So let's simplify our like terms. I know that negative 7 root 2 and plus 7 root 2, those are going to cancel out. And then 49 minus 2 on the bottom is just 47. And then on the top, we can't simplify those like terms. Those are not like terms, so it's 21 minus 3 root 2. And that is our rationalized value so that there's no root in the denominator. Okay, last one is, what if I have to solve where it looks like this? So I can see that there's a squared on the x, but there's no other x value. So what I'm going to do is I'm going to solve for x by getting x by itself. So I'm going to minus the 5 over, and I'm left with 3x squared equals 36. To get that x by itself, we first have to deal with this 3 in front, so we're going to divide the 3 out. We're left with x squared equals 12. And now I'm going to take the square root. Now here's a kind of a special thing. If you have to take the square root, if you take the square root, it must be either positive or negative. So when I write the square root, it's got to be plus or minus. So we know that squared and the root cancel out, so we're left with x equals plus or minus the root of 12. And you can just leave it like that. Okay? All right, guys, that's it for today. I hope you have